Today we are going to present our assignment titled Analysis of Electrical Signal Characteristic and Practical Simulation using Multisim software. And next, we are going to continue with introduction. This assignment focuses on key concepts in electrical engineering and their real-world applications, including audio, volume control with potentiometers, their relationships between RMS and peak voltages, the behavior of AC circuits, and the societal and environmental impacts of projects like the Bakun. Using theoretical analysis and practical tools like Multisim, it combines calculations, simulations, and evaluations to deepen understanding of electrical systems and their design, while fostering awareness of their broader implications.
Hi, I'm Siti Rasha Abdul Aziz. We continue this presentation on how a volume control potentiometer works. So the purpose is the potentiometer is used to control the loudness of sound in an audio system by adjusting the range of the electrical signal reaching the speaker. So the loudness depends on the amplitude, which is higher amplitude produces louder sound waves, while lower amplitude creates quieter sound waves. So how it works? The potentiometer operates as a variable resistor that regulates the voltage and current in the circuit. It adjusts the amount of the electrical signal being passed to the speaker, which directly impacts the loudness. So for the turning the knob, increase resistance. This reduces the current and voltage resulting in a quiet sound. For the decreased resistance, this allows more current and voltage to flow, producing louder sounds. So the key mechanism, the potentiometer has three terminals. So for firstly is input terminus, which is receive the audio signal usually from an amplifier. Secondly is ground terminal, which is acts as the common reference point in the circuit. The lastly is output terminal sends the adjusted signal to the speaker. By verifying the resistance between the input and the ground terminus, the potentiometer controls the amplitude of the signal reaching the speaker. This process ensures the speaker produces a sound at the desired loudness. So the loudness control amplitude relation. A higher amplitude electrical signals means a more intensive sound wave which produce louder audio. However, a lower amplitude signal means a weaker sound wave resulting in quiet audio. The potentiometer changes the signal's amplitude by adjusting the circuit resistance. So what is the importance? The potentiometer provides users with a precise control over sound value, allowing them to adjust it for comfort or specific needs. It also plays a crucial role in ensuring the audio system delivers clear and balanced sounds to tolerate to the listener's preferences. Along with amplifiers, the potentiometer ensures that the signal range is appropriate for driving the speaker without causing distortion or damage. That's all for me. Thank you.
So nice. My name is Siti Nofara binti Muhammad Syahril. My matric number is B0622100045. My part is questions 2. So, questions 2 is about RMS. RMS voltage is a measure of the effective value of an alternating voltage. It is the equivalent direct current, which is DC, voltage that delivers the same power to a load as the alternating current, which is we call it as AC, and the voltage goes over a full cycle. In addition, the peak voltage is the maximum instantaneous value that an AC waveform achieves. This value can be positive or negative depending on the directions of the voltage at a given moment in time. So, the maximum amplitude of a sinusoidal waveform corresponds to the highest points on the curve. In a complete cycle, the voltage oscillates between positive peak and also which is the maximum positive value, and negative peak, which is the maximum negative value. So The relation to RMS voltage is that the peak voltage is always larger than the RMS voltage. Peak voltage also important for understanding the maximum stress on components like capacitors, insulators, and other electronic devices. It defines the extreme value that electrical devices must withstand. So next, I'm gonna talk about difference between RMS voltage and peak voltage. First, about definitions. So RMS represent the effective or equivalent DC voltage that delivers the same power as the AC waveform. Meanwhile, peak voltage represents the maximum instantaneous amplitude of the AC waveform. It can be positive or negative. So next is power relevance. RMS determines the power delivered to a load and is used for practical power calculations. Meanwhile, peak voltage does not determine power but shows the extreme voltage values the system reaches. So we move to another difference. So next is time averaging. RMS has averaged the energy content of the waveform over a complete cycle. Meanwhile, peak voltage does not average value. It measures the maximum voltage at a single point in time. So last is practical usage. RMS voltage is used in a power system to describe effective voltage. For example, 120 volts or 230 volts household voltage. And the peak voltage is important for assessing the maximum stress on electrical components.
I'm Izzati. Now we move to the Bakun Dam controversy. The Bakun Dam is one of the largest hydroelectric projects in Southeast Asia located on the Balui River in Sarawak. The Bakun Dam project was first proposed in the 1980s as part of Malaysia's plan to develop its energy sector and boost industrialization. The dam was envisioned as a mega project capable of producing 2,400 megawatts of electricity, making it one of the largest dams in Asia. The project was eventually completed in 2011 at a cost of approximately 7.3 billion ringgit Malaysia. One of the most significant criticisms of the Bakun Dam is its environmental impact. The dam submerged an area of about 700 square kilometers of tropical rainforest and ecosystem home to diverse flora and fauna, some of which are endemic to the region. The effects of deforestation and flooding associated with the construction of the dam have disrupted the natural balance of the environment and caused a loss of biodiversity. The dam has also impaired the Balui River's hydrology, affecting fish population and water quality downstream. Next, the controversial issues of the Bakun Dam is the displacement of the indigenous people. Approximately 10,000 people, primarily from the Kayan, Kenyah, and Penan ethnic groups, were displaced to make way for the dam. Many relocated families were dissatisfied with the minimal compensation, terrible living circumstances, and loss of valuable land and natural resources critical to their livelihood. Then, controversial issues of the Bakun Dam on the economy is economic feasibility and governance concerns. Initially, the dam was intended to supply electricity to peninsular Malaysia via undersea cables. The project has also been marred by allegations of corruption and mismanagement. The high cost of the project, coupled with its underutilization, has led some to describe it as a white elephant that burdens taxpayers without delivering commensurate benefits. Last, the Bakun Dam causing a balance of development and sustainability. Proponents of the Bakun Dam argue that it has the potential to drive economic development in Sarawak by providing cheap and abundant electricity. However, critics contend that this vision has yet to materialize fully and that the social and environmental costs have not been adequately addressed. Balancing development with sustainability remains a key challenge for large infrastructure projects like the Bakun Dam.
My name is Pei Ying. Today I will be presenting the half-cycle average values of the voltage across R1 and R2 in this circuit. First, let's break down the key components of the circuit. The voltage source is 120 watt meter, with R3 having 30 watt meter and R4 having 65 watt meter. Next, let's calculate the voltage at R1. We already know that the circuit is a combination of series and parallel elements. To find the voltage across R1, we subtract the voltage across the parallel section from the voltage source. This gives us 55 watt meter. For R2, we can see that R2, R3, and R4 fall from a parallel circuit. So the voltage across R2 will be the same as across R3 and R4. To find the voltage at R2, we subtract the voltage across R3 from R4, which gives us 35 watt meter. Now, let's calculate the current across R1. Using Ohm's law, V equals to I times with R. We multiply the voltage by the resistance and find the current through R1 to be 0.117 ammeter. Similarly, the current across R2 is 0.035 ammeter since R2 and R3 are in series. The current through R3 is the same as the through R2, so it is also 0.035 ammeter. Next, we can calculate the resistance of R3. Using Ohm's law, resistance is equal to voltage divided by current. This gives us resistance of 857.514 ohms for R3. For the current through R4, we subtract the current through R2 from the total current, which gives us 0.082 ammeter. Finally, the resistance of R4 can be calculated in the same way as R3, and we find it to be 792.82 ohms. After that, here's got two figures. In figure 1, we can see the wattmeter and ammeter across the circuit. In figure 2, the voltage value across each resistor are shown. Next, let's calculate the peak voltage for R1. Using the formula Vp equals to Vrms times with square root 2, we find that the peak voltage at R1 is 77.78 watt meter. For the half cycle average voltage at R1, we use the formula V average equal to 2 divided pi times with Vp, which gives us 49.52 watt meter. Similarly, for R2, the peak voltage is 49.5 watt meter. Using the same formula, the half cycle average voltage at R2 is 31.51 watt meter. Let's conclude our calculation for R1 and R2. Now I will pass the presentation to Ling Ling. My name is Pei Ying. Today I will be presenting the half cycle average values of the voltage across R1 and R2 in this circuit. First, let's break down the key components of the circuit. The voltage source is 120 watt meter, with R3 having 30 watt meter and R4 having 65 watt meter. Next, let's calculate the voltage at R1. We already know that the circuit is a combination of series and parallel elements. To find the voltage across R1, we subtract the voltage across the parallel section from the voltage source. This gives us 55 watt meter. For R2, we can see that R2, R3, and R4 fall from a parallel circuit. So the voltage across R2.
Hi, my name is Liling. Today I will be presenting on question 5, where we analyze the maximum and minimum values of a sine wave reading on a DC level. This topic is crucial for understanding waveform characteristics in electronics. Let's start with the key concept. We are given that a RMS value of a sine wave is 10.6 watts and a DC level is 24 watts. Our objective is to calculate the maximum and minimum values of a resulting waveform and validate this result using multisim software. Here is how we calculate this value. The formula for maximum and minimum values are: maximum value is the DC level plus the peak voltage, and the minimum value is the DC level minus the peak voltage. To find the peak voltage, we use the formula, which is peak voltage equals the RMS value multiplied by the square root of 2. Substituting 10.6 watts for a RMS value, we calculate a peak voltage of about 14.99 watts. Adding and subtracting this from the DC level of 24 watts gives us a maximum value of 38.99 watts and a minimum value of 9.01 watts. The circuit schematic in Multisim demonstrates the setup for analyzing a sine wave with a DC offset. The circuit consists of an AC voltage source, which is V1, generating a sine wave with a peak voltage of 14.99 watts and a frequency of 1 kilowatt hertz, and a DC voltage source, which is V2, providing a 24 watts offset. These two sources are connected in series, creating a combined waveform. A 1 kilowatt ohmmeter resistor complete the circuit and help the independence matching for accurate measurement. A voltage prompt, which is PR1, is placed across the resistance to capture the output waveform. The circuit is designed to observe the effect of adding a DC offset to an AC sine wave. The oscilloscope displays the resulting waveform, which oscillates between about 39 watts for the maximum and 9 watts for the minimum, matching the theoretical calculation. This setup illustrates the interplay between AC and DC sources and validate the expected behavior of the waveform. Thank you. Next, the waveform output on the oscilloscope represents the combined signal of a sine wave with a DC offset as observed on the oscilloscope. The sine wave is generated by the AC voltage source with a peak amplitude of 14.99 watts and a frequency of 1 kilowatt hertz, while the DC offset shifts the entire waveform upward by 24 watts. As a result, the waveform oscillates between a maximum voltage of about 39 watts and a minimum voltage of around 9 watts. This value aligns with the theoretical calculation, confirming the accuracy of the setup. The graph visually demonstrates how a DC offset affects an AC signal, shifting its baseline while maintaining the waveform's periodicity and amplitude. This output validates the principle of waveform superposition, where the AC and DC signals combine to form a new waveform. Thank you.
To conclude our presentation today, this assignment helped us learn important electrical engineering ideas and how they apply in real life. We look at audio control, voltage, AC circuits and projects like the Bakundam. Using calculation and multisim, we check our results and improve our problem solving. It showed why theory, practice and ethics matter in engineering. That is all from us. Thank you for listening.